This is Sheikh MD Akhil. I am the lecturer of NS Polytechnic College. Today my topic is Vapor Compression Refrigeration System. At first, I introduced the contents of these topics. At first, I discussed the various components of VCRS, the short form of Vapor Compression Refrigeration System. Next, I discussed the TS and pH diagram of the Vapor Compression Refrigeration System. Next, I discussed the comparisons between the reverse Carnot cycle, and Vapor Compression Refrigeration System. Vapor Compression Refrigeration System. These three of this content we will discuss. Next, I will draw the various components of Vapor Compression Refrigeration System. First, we need a compressor. Because the compressor is the heart of the any refrigeration system. And the compressor has two ports. First, it has inlet ports. And the second is outlet ports. The inlet ports are came from a device that is called the evaporator. And it is also a heat exchanger. Here the heat transport takes place from refrigeration space and the evaporator coil. Next, the output of the compressor will go to the next device that is called condenser. And it is also a heat exchanger. Here also the heat transfer takes place from the high temperature to low temperature. Next, the device is connected to a valve that is called the throttling valve. The symbols of this throttling valve is like that. After that, this whole process will go to the again evaporator. Here we see the whole Vapor Compression Refrigeration System works on two pressures. The higher pressure is called as condenser pressure, and the lower pressure is called as evaporator pressure. And the compressor is used to increase the pressure and temperature of the refrigerants to evaporator pressure to condenser pressure. And the expansion valve is used to decrease the pressure from condenser pressure to evaporator pressure. Now, I numbering the whole system that I say that 1, 2 each compressor, This is compressor. 2, 3 is called as condenser. 3, 4 is called as expansion valve. Expansion valve. And 4, 1 is called as evaporator. Now I discuss about the TS and pH diagram to understand the watt input of the compressor and to understand the refrigeration effect or desired effect or heat absorption capability of the evaporator, and also I discuss the coefficient of performance of the vapor compression refrigeration system by using the TS and pH diagram. So at first we need to the board of TS and pH diagram. At first we draw the TS diagrams, that means temperature and entropy diagram. Temperature and entropy diagram. Temperature entropy diagram. Here we say that the vapor compression refrigeration system, and the basic concept of the vapor compression refrigeration system is here the phase change occurs of the refrigerants. That's why we need a vapor characteristics curve of any refrigerant. Each like R11, each like ammonia, each maybe the water, anything. That's why we need a vapor characteristics curve that represent the vapor or saturated liquid and saturated vapor characteristics. So at first we consider any refrigerants as like ammonia, R11, R12, anything, and every refrigerant has individual vapor characteristics curves. So at first we show the vapor characteristics curve, and this is the I consider any refrigerant, and this is the vapor characteristics curve. If we draw in TS diagram, then it looks like that. Here we see that the sharpness of the liquid line is greater than the sharpness of the vapor line, because the specific volume of the liquid with the temperature increase, the specific volumes of the liquid increase more or less than the vapor. That's why the sharpness of the liquid line is more than the vapor lines. Here this point is called as critical point, and this whole line is called as saturated liquid line, and this whole line is called as saturated vapor line. After that, we prove the process takes place in the compressor in TS diagram. Here we see the point 1, and we have to understand what is the point 1 in the TS diagram. At first, we know the compressor is mainly used to compress the gas or vapors. If any liquid particles is present in the vapor or liquid mixture, then the compressor blade is erode. So, at first, we consider that one point is it may be the lie on the saturated vapor line, or it may be lie on the this superheated regions. At first we consider this one point is lie on this line. On this line, this is the one point. This is the saturated vapor coil. After that, the compressor is compressed the refrigerant and the line is vertically upward. That means the pressure and temperature is increasing during this compression process. Vertically upward lines, vertically upward straight lines. This is the 1, 2. This is the 1, 2. After that, the refrigerant or the compressed refrigerant, after increasing the pressure and temperature, it will go to the condenser. And condenser is a heat exchanger, but the heat transfer takes place from higher temperature to environment. That's why the temperature gradually falls. Temperature is gradually fall, and the compressed vapor converted into the saturated liquid. At first, 2 to 2 dash it reject the sensible heat of the refrigerant. After that, 2 dash to 3, the refrigerant reject the latter heat and it converts into the saturated liquid. Next, the refrigerant goes to the expansion valve or throttling valve. What is the function of throttling valve? The throttling valve mainly do to reduce the gain pressure and discharge to the evaporator pressure. That means here only the pressure is gradually decreased, but enthalpy is constant during this throttling process. That's why it is called the throttling valve. And here in TS diagram, it shows like that. But the entropy is increasing. But the entropy is increasing. And this whole process, the whole process, we shown as an anti-clockwise direction because the whole system is power consuming device. That's how it shows like anti-clockwise rotations. And here we shown here the compressor, and the compressor we have to work done on the compressor. That's why the arrow headed on the compressors. And here also we have to work done on the compressor. That's why the arrow is along the cycles, not outside the cycles. It is inside the cycles. Next, the device condenser. Condenser here, the heat rejection takes place and it is from the system. That's why it is outside the system. Here also we saw the rejection of heat outside the cycle. And next one is the throttling valve, and throttling valve only the pressure is decreased and here the enthalpy does not change. Okay, that's why it is so a dotted line. And fourth one, here mainly the desired effect will take place, and this device is named as evaporator. And here the refrigerant is converted from liquid to gas, and to converting from liquid to gas it requires latent heat, and latent heat collects from the refrigerated space, and the arrow is shown to the system or inside the system. Heat absorption takes place, and here we show this diagram the desired effect is shown into the system like that. After that, we draw the pH diagram of the systems. pH diagram to understand the pressures and enthalpy of the system. So at first we draw the pH diagram to understand pH diagram. P for pressure or H for enthalpy. A vertical line represents the pressure lines, and horizontal line represents the enthalpy lines, and vertical lines vertical lines this is the vertical lines and this is the horizontal lines. Now the vapor compression refrigeration systems. In this system, the refrigerants the usable refrigerant is NH3 R11 or R12, and the phase change takes place during this process. So we have to meet the pH characteristics curve, and the pH characteristics curve look like this. And this is the tip of this pH curve. This is called as critical point. And this whole line is called as saturated liquid line. And critical line right hand percent is called as saturated vapor line. So here we discuss the pH diagram of this whole vapor compression refrigeration system. Now we come to the pH diagram. At first we have the point 1, and this point will start from the saturated vapor point, and here also we started these lines on this point, a saturated vapor point. After that, the compression takes place. We know the point of compression is takes place, the enthalpy is gradually increased, and it will like that. And the 2 point is shown here, and this is the superheated region. Here pH diagram we also see the 2 point of the compressor is lie on the superheated regions. So here also we represent the 2 point on the superheated regions, not the wet regions or not the wet regions. After that, the heat rejection takes place in constant pressure. That's why this line is vertical. This line is vertical, and the superheated gas or superheated refrigerant converts into the liquid. And this point is end to the 3 point, and 3 point is lie on the saturated liquid line. After that, the isothermal process is takes place to the throttling valve. That's why this totally vertical lines, and here we see that the enthalpy of the inlet and enthalpy of the outlet of the throttling valve is constant. And next process, evaporator. Evaporator also the constant pressure heat rejection takes place. That's why it is shown again a horizontal line on the pH diagram. This is the whole of the pH diagram of the vapor compression refrigeration system, and this is the various process of the vapor compression refrigeration system. Again, I say that 1, 2 is isentropic expansions, 2, 3 isobaric heat rejections, and 3, 4 is isenthalpic process, and 4, 1 is isobaric heat absorption. Isobaric heat absorption. Next, I will discuss from the TS and pH diagram the coefficient of performance of the vapor compression refrigeration systems and the required work input to continue this whole process. So at first we write down the four process. 1, 2 is takes place on the compressor and it is called as isentropic. 1, 2 is isentropic compressor. And during this process, the entropy is constant. That's why S1 equal to S2, but the enthalpy is increased. And this process also called as reversible adiabatic process. And here the required work input to the compressor equal to the outlet enthalpy of the compressor means H2 and required H2 minus inlet enthalpy of the compressor. This is the what input required to run this compressor. The process takes place in condensers, and the process is isobaric process. Isobaric process means here the pressure is constant, and the whole process is takes place in condensers, and the rejected heat we calculate from this formula. The outlet, the inlet enthalpy of this refrigerant when it enters to the condensers, and outlet enthalpy of this refrigerant. This is the heat rejected by the condensers. After that, 3-4 is called as throttling process. 3-4 is called as throttling process. Here the inlet enthalpy of this refrigerant is equal to the outlet enthalpy of this refrigerant of the throttling valve. Okay. This therefore is also called as isenthalpic process. Isenthalpic process. Next, the refrigerant will go to the evaporators, and heat absorption of the by the evaporators. We write this from the inlet enthalpy of this refrigerator is H4 and the outlet enthalpies of this refrigerator is H1, and the outlet enthalpy of this refrigerator is greater than the inlet enthalpy of this refrigerator, because here the refrigerants absorb the rapid heat to convert liquid into the vapors. That's why we write this desired like this: H1 minus H4 kilojule per kg. After that, we know here. After that, we calculate the coefficient of performance of this whole process. We know any refrigeration system, the coefficient of performance is a great parameters to analyze any refrigeration system. You know the formula of the coefficient of refrigeration system is right the desired effect in numerator and the watt input in denominator. It is right also in this form. The desired effect means the watt, the absorbing heat by the evaporator, and the watt input we write also in this form. The heat rejections watt input. Okay, watt input is not like that. After that, we know all of these parameters from the different process. First, we know the absorbing heat by the evaporators. We use this formula H1 minus H4, and watt input to this watt inputs to run the compressor requires we get from this formula H2 minus H1, and this formula we also write like this: H1 minus H3 by H2 minus H1, as the H3 is equal to the H1. That's why we write this formula like this: H1 minus H3 by H2 minus H1. This is the whole vapor compression refrigeration system. Now, next we discuss the comparison between the vapor compression refrigeration system and reverse Carnot cycle. We already take a class before this day, the reverse Carnot cycles. Now I compare it. At first, left side we write the reverse Carnot cycle, and right side we write the short form Vapor Compression Refrigeration System. So at first we saw that the TS diagram of reverse Carnot cycles look like this. If this diagram of this vapor compression refrigeration system look like this. Is a rectangular form, and today we see the DS diagrams of the vapor compression refrigeration systems look like this. One, two, three, four. And here we see, if we use the reverse Carnot cycles in domestic refrigerator, the compressor blade will damage quickly, because in reverse Carnot cycles it works between two temperature limits. First is lower temperature limit, that is called the evaporator temperature, and the upper temperature limit, that is called the condenser temperature. But in vapor compression refrigeration system, it works between two pressure limits. The lower pressure is called as evaporator pressure, and the higher pressure is called as condenser pressure. And the reverse Carnot cycles we have to analyze it, because it gives the maximum coefficient of performance. It gives the maximum coefficient of performance it gives less coefficient of performance. But in reality, we see that it is a hypothetical cycle. It is a hypothetical cycle, or we do not use these cycles in any refrigeration system like domestic refrigerator or air conditioning system, and it is the actual practical cycle. It is a actual practical cycles. We do not use these cycles in refrigeration system because the compressor will damage. Compressor will, if you use these cycles, compressor will damage quickly. And here, if you use the Vapor Compression Refrigeration System, compressor will not damage quickly, because here we see when the inlet enthalpy of the gas, if you use the reverse Carnot cycles, is the combinations of the vapor and the water, vapor and the gas, or vapor and liquid molecules. That's why the blade particles strikes the liquid molecules and it erodes the blade. That's why compressor will damage quickly. And here the one point registers from the saturated region or the saturated liquid line. That's why this compressor will not damage quickly. But every system has a lifetime. Okay, but it takes its the service provided by the compressor used in vapor compression refrigeration system is more than the reverse Carnot cycles. We analyze it from this TS diagram of reverse Carnot cycles and TS diagram for the vapor compression refrigeration cycles. Okay. Thank you. Today my topic is over. Next I will continue further more from this. Okay.